So hello everyone. We are Tim and Marguerite. We are two French students. We are here for an internship for the summer. We've been here for like 3 or 4 months, and we worked on the Boris project on this dancing hexapod. So today we will present you a bit the project, and we will show you a short demo of how it works.
Yes, so let's start by explaining. So the Boris project, the goal is quite simple. In fact, the idea is to make a robot to dance to music, having a robot dance to music being untrained by external stimuli. But there is this word here. So it's also collective robotics. So the long-term goal of this project is to have multiple robots dancing and being able to study the behavior of multiple robots. So yeah, let's start by talking about how it moves.
So in this robot there is a controller. So it's a central pattern generator. So it's bio-inspired. It's a bio-inspired neural network. And it's evolutionary robotics, so it's evolutionary algorithm. So we create hundreds of different CPGs, and we select the best according to certain fitness functions. Central pattern generator are in nature used to generate rhythmic outputs. So it's what allows animals or humans to breathe or to walk automatically, and it can also adapt to external environment.
So now that we have a bit of context on how it works, let's talk about the elephant in the room, or more exactly the hexapod in the room. So yeah, that's the hexapod. The hexapod is based on a design that is open source. It has been designed, and yeah. So on GitHub, you can find the files of every part of the robot. In our case, we did modify a bit the parts to fit better the electronics that we fitted inside. But yeah, the parts can be either because there are off-the-shelf parts. But on the hexapod, you can see that there are parts that are 3D printed here in the lab over at the IFI department. We also used CNC machining to cut those transparent plates to hold the legs together. So yeah, that's the hardware part. But it's not only that. In the computer, in the hexapod, and with the computer. Oh, yeah, you're right. We have, yeah.
We have some sensors in the robot and outside of the robot that allow the robot to adapt to the external environment. We have a microphone here that you can see that provide the audio input to the robot on which he will dance. And we have also in the robot an IMU. So IMU means inertial measurement unit. So it can measure the orientation or acceleration of the robot. So here we use the orientation, the front and side orientation. It allows the robot to be more stable and to adapt his behavior if he falls or anything.
Yes. So yeah, the controller is based here, and then it controls the robot. So now that we have the controller, now that we have also the hardware part, the microphone for the external input, we just need to do the evolution of the controller on this magnificent robot, right? Right? Well, not exactly. because when tuning and trying new controllers on the robot, sometimes it can some behaviors can happen. Here, yeah, so it was a hexapod, not a 5-legged robot, and that's a case where we don't want the real robot to be broken. So trying things on the real robot can be dangerous for the robot itself. So not ideal. Also, it takes a lot of time to rerun all the different controller, because, as Marguerite said, the evolution works when we have a lot of individual in one population, and if we had to evaluate every individual with one robot, it would take too much time. So we do it in simulation, right? So in our case, we used the game engine Unity. You might have heard of it, and that so that that simulation, we can import our robot in the simulation quite easily thanks to the 3D files that I showed you just earlier, and then yeah, we can have the robot dancing in simulation. Here in simulation, the iteration will be quicker. We can run multiple individuals at the same time using multi-threading. But yeah, so the idea is now we can train the controller, and here it's working, but there is no audio input, right? So with the CPGs, we have this this oscillation that is built in this controller, and this behavior is linked to the controller used. Yeah, so let's try to see how it performs with music. So it transitioned from its bass behavior to one where it tries to sync to the music, and it's not tempo dependent, so we can change also the kind of input. It's not always clear when what he is doing, but we get the general idea, right? So now it's working. We can gather the data with the help of the game engine, because it's very easy to gather data from a simulator. You don't have to physically put a sensor somewhere. Here, for example, we have the X and Y coordinates of the robot in simulation over time, so for one particular CPG. So yeah, now that we've trained everything, we've measured everything, we can just put it on the robot and call it a day, right? Not quite right. Yeah, because we don't know if what we used in simulation is really representative of what's happening in the real life. So we need to find a way to see if this simulation is really close to reality. In our case, so that's the position in space. So to do that in the real life, we used so the Qualisys system. So that's a motion capture system. So it tracks markers. So you can see the markers here in space with a sub-millimeter resolution. And the cameras are around you. You can see all the cameras here. And then with those cameras, we can run the CPG on the controller on the real robot and see if what the robot is doing.
So yeah, here is the trajectory of the real robot in the room. So it's a bit chaotic, but we can see a pattern here. And we can see, comparing the real robot and the simulated one, that the global pattern is quite the same. and now that we can plot all the data together, the pattern is the same but with multiplier factor. So yeah, the real robot goes slower than makes less distance than the simulated one. In this case, for this CPG in particular.
Yeah. So we've promised a live demonstration. I think it's time to do this demonstration. So maybe we will do the same thing as what I showed you in the simulation. So at first, I'm going to ask you to not make any noise. That I mean, you were already doing sounds. So that's right. We are going to try that. We will see that the robot will move in its base behavior. And then we are going to clap in our hands and make the robot dance. Okay, so are you ready?
Yeah, it's initializing.
Robot is blinking. That's the basic pattern, and then we can so it can so the control can saturate, and sometimes when there is too much noise, it's just stuck. So that's what we saw. And then if we stop making sounds, then it's going to transition back to the previous one. So just okay. So, and now it's going to. Thank you for your attention. Yeah, now if you have questions,
we have about 10 minutes or so for questions. Yeah.
I really like the notion of the central pattern generators. I've seen them for locomotion and quadrupeds, like for four-legged things. This algorithm that you're using, is it scalable to other setups and for like bipedal movement or things like this?
So right now it has been used with quadrupeds and hexapods. So it depends on the. I mean, so the CPGs are kind of building blocks, and then if you can design a controller that will work for the number of joints that you want. So yeah, it will work with if the controller is designed with one a robot in mind, then it can be
okay. Skilled. Yeah. Okay. Nice. And second question, if I can. Have you thought about applications for maybe rehabilitation? Like one impressive direction of using this kind of robotics steered by CPGs is for exoskeletons or prostheses, things like this. Have you talked or thought about human-machine interaction, so extending it into more prosthetics or things like this? Is that an idea of this project, or is that the direction where this project is going?
It's not in the that was not the goal
okay.
from but I'm sure that there are some. I mean, there are in this project there is also this idea where we will have interaction with a human and robot interaction, but I don't think that it was for exoskeleton, but more having reacting, so that the collective behaviors would be possible to see them, to observe them between robots, but also I don't know, maybe have humans and try to see how it maps. So
no, great, thank you. Yeah, more in group behavior or how a group ensemble works together.
Yes, but the idea was
so. Thanks. I'm curious about the management of noise, if there is any, because I saw that it's very sensitive to the sound, and there are some things happening there. So is there something like that, like you want to have kind of threshold to when to dance, and or how to respond to these minimal variations of sounds?
So I implemented a dynamic range compressor for the audio input, but it's supposed to reduce high-level sounds and increase low-level sounds. But the parameters are not set very properly yet, and also it was the first time we tested it with that amount of people around. So when we tested it, it was just with either a metronome or just us two clapping our hands. So it can influence the behavior, and also the fact that I think that the CPGs were trained with one level and a certain range of BPMs, so it can also influence the behavior.
But that's just in the audio side, so in the side of the robot that is capturing the audio, there's not any filtering.
Yeah, there is a filtering, but it's part of the evolutionary process.
Okay.
And so it depends on how the robot and the CPG evolved, and I didn't work on that part, so maybe my answers are not that that precise.
So related question: have you had a chance to look at the CPG that evolved as the sort of optimal CPG, and what is that evolutionary landscape like, and can you reverse engineer anything about the CPG to kind of figure out how it's solving the problem?
So the CPGs. So every time we run one evolution, we end up with a lot of CPGs. Then we have those fitness functions, and we just depending on the evolution we're doing, then we will select the ones with the best. But there are a lot of different CPGs, so we try to look at different ones to see how they behave, and the behavior is very, very different from different controllers. And then so the environment the evolution is run on the simulation you just saw. So by environment, if it's what you're asking, it's like flat ground.
No, I meant like the landscape of the evolutionary optimization problem. So you've got a state space of the your genome essentially. What parts of the genome did it optimize most? What parameters were most important for creating a controller that was robust and etc.
And for that, I think that the best would be to ask Alex Szorkovszky and Kyrre Glette, because they worked on this side. We worked more on the so we didn't do the designing of the CPGs.
Okay,
question. Any ideas what might be the most important factors that get the difference between the actual real behavior and the simulated? And how many of them could be improved?
Yeah. So what I think from what I've tried with the simulator, the main difference is the friction with the feet on the ground. So it's not doing the same thing at all. So I would say that's the thing that causes the biggest difference. But yeah, maybe there are other things too. And in order to solve that problem, we so it's a work in progress. But the idea is to say, okay, if we say that if this friction we cannot model the friction very well, then during the evolution at every regeneration we would drastically change the friction, and then the individuals would have to adapt to every kind of friction. And then by doing that, so that's called domain randomization. You randomize one part of the parameters. Then hopefully the simulation and the reality, even if it's still far apart, the controller will still be good enough and robust in the real life. So that's something that we are going to try to explore more in the future. Yeah.
And one more question: is the actuator noise included in the simulation? Like because
the sound, yeah. No, but yeah, that's.
Yeah, the first idea was to put the microphone directly on the robot. So we had a very small microphone adapted to Arduino, and it appeared that it was not a good solution because it's very, very loud, and so we decided to put the microphone far from the robot so it doesn't really detect the sound of the motors. So that's maybe it's the solution for now, but maybe it could be interesting for other applications to have the microphone directly on the robot and filter the noise of the motors.
All right, I think we have to move on to the next demo. Thank you so much.
Thank you.